Hey there, this is the first lecture video for Chapter 6. We're dealing with lots of unfamiliar terms this time, so make sure you catch those on your lecture notes and understand how they fit into the formulas we're working on. There's also new notation to add to your collection. Also, more and more, I'm depending on you already being familiar with how to use your calculator. So if you're still struggling with that, come into office hours or stop into the tutoring center to get some help catching up. Okay, let's dive in. Welcome to the lecture video for Chapter 6, Section 1, Confidence Intervals for the Mean, where sigma is known. So far, we've been looking at descriptive statistics, collecting and describing data, learning how to find probabilities, learning how to analyze different distributions. Now we want to know how to use sample statistics to estimate a value of an unknown population parameter. In real life, we don't always have the finances, time, or capacity to take a census, meaning get data on every single person or member of the population every time we want to know something about a large group of people, especially when that group is perhaps the entire country. At best, we can take samples to estimate those unknown population parameters. So in this section, we're going to learn how to find a point estimate and a margin of error. We're going to learn how to construct and interpret confidence intervals for a population mean, and we're going to learn how to determine the minimum size of sample that you need to estimate a certain population. So we'll start with a definition. A point estimate is a single value estimate for a population parameter. The most unbiased point estimate of the population mean, mu, is the sample mean, x bar. Now, we might take a moment here to recall that the average of all possible sample means of the same size, we called that mu sub x bar, meaning the mean of a sampling distribution of sample means. Remember that that is equal to the population mean mu. So what we say is that x bar is an unbiased estimator of mu. Let's do an easy example. A researcher is collecting data about a college athletic conference and its student athletes. A random sample of 40 student athletes is selected, and their numbers of hours spent on required athletic activities for 1 week are recorded. Find a point estimate for the population mean M, the mean number of hours spent on required athletic activities by all student athletes in the conference. So the point estimate is x bar, or the average from our sample. So the average from these 40 athletes is found by finding the total, which is 797, then dividing that by the sample size, which is 40, and we get about 19.9. The point estimate from the mean number of hours spent on required athletic activities by all student athletes in the conference is about 19.9 hours. A logical question to ask at this point is, what are the chances that the actual population mean is equal exactly to 19.9? We only took a sample size of 40, so that might not be a very high number. What would be better would be to have an interval that the true mu could possibly lie within. So to find the interval estimate, we use the point estimate like we just found as the center of the interval, and then we add and subtract something called a margin of error to create the rest of the interval. So here's a quick example. Using the data from the college athletes and a margin of error of 2.1, create an interval estimate for the population parameter. We're going to use the point estimate as the middle of our interval, and we said that the value was 19.9, so that's our x bar. Then we add and subtract the margin of error to that value. So we do 19.9 minus our margin of error of 2.1, and we get 17.8, so that's our lower bound of our interval. Then we take 19.9 and add 2.1 and get 22. That is our upper bound of our interval. We can now say that our interval estimate for our unknown population parameter is somewhere between 17.8 and 22. Of course, there's still a chance this interval doesn't contain the actual population mean mu. So the next step is to give some kind of confidence level to our interval estimate, that it contains the population mean. Let's consider this definition and example. The level of confidence C is the probability that the interval estimate contains the population parameter. This is assuming that the estimation process is repeated a large number of times. Say we wish to study the eating habits of a typical American household. Let the random variable x denote the number of meals prepared at home in a week. That is, the possible values of the random variable are 0, 1, 2, etc. up to 21. Assume a margin of error of 2.5 and that you draw 6 samples and come up with the following averages. X bar sub 1 equals 10, X bar sub 2 equals 13, X bar sub 3 equals 12, X bar sub 4 equals 14, X bar sub 5 equals 13.5, and X bar sub 6 equals 17. Let's graph those. The first one, we count from the mean, which is 11.5, and we put our center at 10. We have to count over to the left of 11.5. Then we subtract the margin of error on the left of that, and we said the margin of error was 2.5. So we subtract 2.5 from 10, and we would get our lower bound around 7.5. Then we add 2.5 to the right of that, and we put our upper bound at 12.5. Our next one has its center at 13. So we subtract 2.5 from 13 to put our lower bound at 10.5, then add 2.5 to get our upper bound at 15.5. Our next one has its center at 12. We put our lower bound 2.5 below that, and the upper bound 2.5 above that, and so on and so forth. You can see that that is what we've done for the rest of these. So if the true population average, mu, equals 11.5, and the margin of error is 2.5, look at where the true population average of mu lies amongst our intervals. Well, that is interesting. 2 of the sample intervals do not contain the true value of the parameter. So what do we conclude from this? We need a way to measure how confident we are that the interval estimate contains the parameter. In this course, we're only going to concern ourselves with 90, 95, and 99% confidence levels. Notice that all the samples put together in the previous example created what we call in an earlier section a sampling distribution of sample means. If the size of each sample is greater than or equal to 30, what does the central limit theorem say about that? It says that the sampling distribution of sample means will be approximately normal. Okay, so that makes a really important point. The level of confidence C can also be interpreted as the area captured beneath the standard normal curve. And that area is going to be captured between 2 points that we call critical values, negative Z sub C and positive Z sub C. Critical values separate probable sample statistics that are inside the blue area from improbable sample statistics that are on the outside, the TN area. Let's do a quick example. If our level of confidence is 90%, meaning I want to be 90% confident that the interval estimate is capturing the true population parameter, I want 90% to be captured within the middle of the standard normal curve. So that means I've got 2 critical values on the inside. I want 0.9 area. That means I will have 10% left over to go on the outside of this captured area. So 5% on either side, or 0.05, because my graph is symmetrical. At this point, we can use the inverse norm function on the calculator to figure out the z-scores that would be at these points. So I would press the second button, then the vars button, then scroll down to inverse norm and plug in 0.05 to give me a z-score of negative 1.64. Now the great thing about z-scores is that they're from a symmetric distribution. So I know I can change the lower critical value, which is negative, to a positive and use it for the upper critical value. So the positive Z sub C score, the positive critical value, is going to be positive 1.64. Now, why are we wanting these values? What is their importance? They give us a cutoff point between what we consider probable sample statistics and improbable sample statistics. So if I take a sample and my values are outside these critical values, then it's probably a biased sample, or the technique we used was not properly executed. Remember, this is all about sample statistics. This is not about population parameters. This is about trying to use point estimates to create an interval with a level of confidence so that they are good estimators of the true population parameter. Okay, so now we move into thinking about if there is a difference between what we come up with in sampling and what the true population parameter is. How do we go about finding that difference? By definition, the difference between what we measure and what the actual value is what we call the sampling error. For mu, you find this by subtracting x bar minus mu. Now mu is generally unknown and x bar varies sample to sample, but we can still calculate a maximum value for the error simply by defining the level of confidence that we want to use and by taking a sampling distribution. Here's how we do this. The margin of error, sometimes you'll see in the text called the error tolerance. We take the critical z sub c value and multiply it by our standard error. Remember, that's the standard deviation of the sampling distribution of sample means, which is the ratio you see here. The population standard deviation divided by the square root of the sample size. This is known as the margin of error for mu when sigma is known. We're interpreting this as the greatest possible distance between our point estimate and the value of the parameter. So before we go on, we need to talk about a few conditions for using the formulas we're discussing. In order to create these intervals, we have to know at least two values. We have to know C, our level of confidence, and we have to know the population standard deviation, sigma. We also have to know that we have done everything possible to ensure that our sample is random. In order to use the standard error formula, the one with the ratio, either the population was normally distributed or the sample size was equal to or larger than 30. This is necessary to use the formula and so that we could apply the central limit theorem, which we will get to shortly. Okay, let's do an example. Use the data in example 1 and a 95% confidence level to find the margin of error for the mean number of hours spent on required athletic activities by all student athletes in the conference. Assume the population standard deviation is 2.4 hours. Okay, it's important to note that we're working with a 95% confidence level here. Because sigma is known, and they said the sample is random, and the sample size is greater than or equal to 30, it's 40, we can use the formula for E, or margin of error. So then we need to figure out what our critical values are. That is defined by the level of confidence that we want to assume, and we're told that we want 95% confidence. That becomes the area that is captured by the standard normal curve. So I put 95% in the middle, and that means I have 0.05 to divide in half to put on each side because this is symmetrical. That means I'll put 0.025 on each side. Be careful when you're dividing there. I can use my calculator at this point and the inverse norm function by pressing second, then vars, then arrow down to inverse norm and put in 0.025 and enter as many times as needed to calculate. It will give you the negative bound, and it will also allow you to get the positive version of that number for the upper bound as well. So there's our z sub c and negative z sub c values, or our critical values, negative 1.96 and positive 1.96. Then we look at the margin of error formula to see what values we need. We need the positive z sub c, so 1.96. We need population standard deviation, or sigma, and the sample size, which was 40. So plug the values in and see what you get. You should have gotten about 0.7. The way you can interpret this is that you are 95% confident that the margin of error for the population mean is about 0.7 hours. Now we have all the ingredients to construct an interval estimate for the population parameter. Here's how we're going to put it all together. A C confidence interval for population mean, mu, is given by x bar minus this margin of error, that's the lower bound. Then mu is captured between that value and x bar plus the margin of error. So this is the full confidence interval. Not just an interval with some given margin of error, but a margin of error that is dependent on the level of confidence that we want to use. So the probability that this interval contains the true population parameter mu is C. It's a C confidence interval. It's also the probability that the interval contains that value. And again, this is assuming the law of large numbers, the estimation that this process is repeated for a large number of samples. Okay, let's go through how to find a confidence interval for a population mean when sigma is known using both words and symbols step by step. First, you want to gather all the pertinent information to your problem and verify that you can actually use these formulas. This means verifying that your sigma is known, that the sample taken is random, that either the population is normally distributed or the sample size is greater than or equal to 30, and write down or somehow note the values you need from your information like sigma and n. Also, have they told you what level of confidence you're supposed to assume? And do you know X bar or do you need to find it? Second, if you're not given the sample statistics, if you're just given raw data points, then you need to find the point estimate, your X bar or sample mean at this point. Find the critical value Z sub C or your critical points or Z scores. You can use your standard normal table in Appendix B or use the inverse normal function on your calculator to do this. But you have to get to that point first. You need to work with the confidence level the problem is assuming. Draw your graph, then figure out how much area is left to either side of the probable area. The area on one side is what you use to find the negative Z-score. Then you use its positive counterpart also. Fourth, find the margin of error. This is a product, but you need to plug a few values in to achieve it. You need to have the following values ready: Z sub C, or your positive Z-score value, sigma, and sample size. Then plug them into the formula. Lastly, find the left and right endpoints to form the confidence interval. This is done by subtracting your result from the last step, your margin of error, from X bar, or get the left or lower bound, and then adding it to the X bar to get your upper bound. The result will be your confidence interval. Let's practice this process with an example. A college admissions director wishes to estimate the mean age of all students currently enrolled in a random sample of 20 students. The mean age is found to be 22.9 years. From past studies, the standard deviation is known to be 1.5 years, and the population is normally distributed. Construct a 90% confidence interval of the population mean age. Okay, so first we need to note important data and ensure that we can use the formulas we need to use. The samples are random, they told us that. Now the sample is only 20 students, but it states that the population is normally distributed, so that's okay. Standard deviation given is 1.5 years, and they have told us to assume a 90% confidence level. Next, X bar is given to be 22.9 years. Okay, step 3 says we need to find the critical values. They expect a 90% level of confidence, which means we need to use 0.05 to find Z sub C. When we do that with our calculator, we get negative 1.64. So our critical values are negative 1.64 and positive 1.64. Next, we need to find margin of error. We've just found positive Z sub C value to be 1.64. We know that sigma is 1.5 and n equals 20. So we can plug those values in and we get 0.6. So that is our value for E, or our margin of error. Now we need to find our left and right endpoints to create our interval. That means subtracting E of 0.6 from our X bar of 22.9 and then adding it to 22.9. We end up with an interval from 22.3 to 23.5. Or we can write it as an inequality like this. Here's how we would state this. With 90% confidence, we say that the true mean age of all students currently enrolled is between 22.3 and 23.5 years old. Here's another way to lay out your process if it helps you. Start with collecting your data at the top, your values for n, X bar, find it if needed, sigma, and find your Z sub C. State the margin of error confidence level. Write your margin of error formula as a product with the values. Then approach the endpoints from each side, subtracting E from left and adding it to the right. You don't have to do it this way, but if you're a visual person and it helps to organize it differently, do that for yourself. You don't have to do it the way that I do it. Find what works for you. Before we move on, let's make a few observations. As confidence goes up, the area under the curve gets bigger. As the area captured under the curve gets bigger and widens, How does that affect the critical values? If you look at this graph, here's what the positive z sub c value is when the confidence level is 0.9 or 90%. When we increase the confidence level to 95% or 0.95, see how that increases? Z sub c value goes up because the area widens. The area beyond it goes down, but the z sub c value itself goes up. If the confidence level goes up again to 0.99, the z-score, or the z sub c value, goes up again. So the positive z sub c score, which is part of the product in the formula for margin of error, and the positive critical value on the right of the graph, goes higher too. As the critical values are going up, that means E gets bigger because of the margin of error formula, because z sub c is part of the formula. It's part of a product which makes the result larger. If it had been part of the ratio, it might have had a different effect, but it's part of a product. As E gets bigger, the confidence interval gets wider because you're subtracting the margin of error from the x-bar or sample mean and adding it to x-bar. So we're getting a wider and wider interval. Here's the kicker. When confidence gets wider, we lose precision, and that's the opposite of what we want to happen when we're gathering statistics. So how do we avoid this? Well, one way is to have a more appropriate sample size. That usually means a larger sample size. How do we figure out what that size is? Well, let's look at one way to do that. To find the right sample size, we can actually use our margin of error formula, but solve it for n. That will give us the optimal sample size, the one that is exactly appropriate for the other variables that you put into the formula. But we have an obstacle. We need to solve this formula algebraically for n. Well, no big deal, right? You're in college now, you can do this, right? Well, no worries. I'm going to walk you through it. So here's our original formula. E equals z sub c times population standard deviation over square root of sample size. Well, the first thing I see, and honestly you could do this lots of different ways, so if you see a faster way, by all means do that. But the first way I see is to divide through by z sub c. Okay, now we want to eventually isolate n, so I'd say we need to get it in the numerator. So let's do that now by multiplying through by square root of n. After that, it's all about isolation. I'm going to do a few things at once in this next step. I'm going to multiply through by z sub c and divide through by e. My last step is to square both sides. And there we are. This is our formula for finding the minimum sample size needed. So given a C confidence level and a margin of error E, the minimum sample size n needed to estimate the population mean mu is this formula. N equals z sub c times population standard deviation divided by margin of error quantity squared. If the resulting answer is not a whole number, we're going to need to round up to the next whole number. And if sigma is not known, you could estimate it by using the sample standard deviation if you have a sample of at least 30. Let's do an example. The researcher in example 1 wants to estimate the mean number of hours spent on required athletic activities by all student athletes in the conference. How many student athletes must be included in the sample to be 95% confident that the sample mean is within 0.5 hours of the population mean? Okay, so the data we need is C, or the confidence level, of 0.95, Z sub C of 1.96, which we would have had to figure out, or we could have remembered after doing this a few times at the 95% level of confidence, sigma of 2.4, which they gave us, and margin of error of 0.5, which we found before. So we plug these values into the formula, and we have 1.96 times 2.4 divided by 0.5 quantity squared, and we get about 88.51. Then, because our result is not a whole number, we round it up to 89. So the researcher needs at least 89 student athletes in the sample. And to come to a practical solution, Relate this to the problem at hand. We know the original researcher has 40 student athletes, so the sample needs 49 more members. 89 is the minimum number to include in the sample. Okay, that is the end of this section. Make sure you got all those terms in your lecture notes and all of that notation, meaning formulas, wherever you're keeping those. Just keep swimming. You're doing great. I'll talk to you in the next video.